The next topic that we're going to discuss is called as the matched filter. And as the name suggests, matched filter is basically a receiver filter that is matched to the transmitted pulse. So the receiver is trying to receive a pulse that has been transmitted by the transmitter, and the matched filter has its impulse response designed in such a way that it is matched to the incoming pulse that was transmitted by the transmitter. And the reason for doing that is we want to maximize the signal to noise ratio at the receiver input. So match filter is one way of doing it, and today we will discuss about the concept of the match filter and what does the impulse response of the match filter look like, and then we will see that eventually show that the signal to noise ratio of the match filter and how it is maximizing that signal to noise ratio as well. So we will discuss about all these things in this video. So first of all, let us consider that we have a pulse that we are transmitting. Let's call this x of t, the pulse on the top here. That is our transmitted pulse. It is having a duration or a width of some tau. So we have on the x-axis here time, on the y-axis is our amplitude of the pulse, so we denote that as x of t. That is our transmitted pulse. It is starting at some arbitrary time, let's say t naught, and finishing off at a time t naught plus tau. So the width of the pulse is tau, so it goes from t naught to t naught plus tau. So that distance is tau. That means half the distance from here to here, that is tau by 2. So let me be very clear. Okay, tau. So that's tau by 2. Okay, so we have this transmitted pulse. Now what the theory of the matched filter says is, we are not going to prove it, but we'll just state it and then write an expression for the impulse response of the matched filter, and then we'll also write the output of the matched filter, the expression for the output of the matched filter. So the theory of matched filter states that the impulse response of the matched filter, impulse response of matched filter is time reversed causal representation of the transmitted pulse. So the first thing we need to notice, time reversed. So the first term that it says is the impulse response is a time reversed and causal representation of the transmitted pulse. So our transmitted pulse is here. Time reversed means we're just going to flip the time axis, so it's going to be reversed in time, so the entire pulse comes to the left side like this here. So this is the time reversed version of the transmitted pulse, which we simply say okay, by the way, that's the origin 0, so that's the origin 0. So this is negative time now. So this is the time reversed version of the transmitted pulse. Now if you see, in the time reversed version, we cannot have this as an impulse response, because it is showing, if this was the impulse response output of a filter, that means it is giving an output before time 0, and that is not possible in the real world. Okay, you cannot have an output before the input. So this is non-causal, so we cannot have x of minus t as the impulse response. So therefore now we need to shift this by a certain amount to bring it on the right side of 0, and that shifted version is basically to make it causal. So we shift this to the right and make it to the right of 0. So we have this here, which is the causal representation. So we have here again on the x-axis we have time, and that's 0, and now it is 0 to some tau. Okay, because the width is still tau, the width of the pulse is tau. and we choose a certain amplitude which is denoted as 1 by tau equivalent. Now what is this tau equivalent? I will talk about that in a little while, and then we will see how it is related to the width of the pulse that is transmitted. Okay, and again we will restrict our discussion to the rectangular pulse of amplitude 1. So if we have this pulse and now we have reversed it in time, and then we have shifted this to the right and brought it to the right side of 0, so that is our impulse response of the matched filter. So that is our h of t. So mathematically we can write this h of t, so h of t to be equal to, it has an amplitude 1 by tau equivalent, and it is x of, this is x of minus t, and this is shifted to the right by some amount which we will denote as td. And now shifted to the right generally is minus because the time axis has now been reversed, so it should become plus, right? So x of minus t plus some shifting that we are doing, which we call as td. And when we are dealing with the rectangular pulse, instead of x of t, we'll write it as p of t, just to indicate that it is a rectangular pulse, which is 1 by tau equivalent p of, so we can write it as td minus t. Okay, minus t plus td. I just rewritten it as p of td minus t. Okay, so this is indicating a rectangular pulse. So x of t can be any pulse shape, but we are focusing on the rectangular pulse. Now the output of the matched filter, so is going to be the convolution with between the input and the impulse response. So that's the impulse response of the matched filter, and that's the input to the matched filter. The input is the pulse that is transmitted, which is what is being received. And again, we are assuming that there is no noise for the analysis. So the ideal analysis would give us the output, which is the convolution of this pure transmitted pulse, uncorrupted transmitted pulse, with the impulse response of the matched filter. So now we have a rectangular pulse as the input and the rectangular pulse as the impulse response. So the convolution of a rectangular with another rectangular is a triangle, right? So as a triangular function. So the output signal, this is y of t, the output of the matched filter. So we call this as y of t, and on the x-axis we have the time. So the output of the matched filter, y of t, is the convolution between the input and the impulse response, which is h of t, that's the impulse response, and I'm going to denote convolution by the star. So convolved with the input signal x of t or p of t, that is, right? So in general it is convolution between the impulse response and the input to the matched filter. Now a couple of things that we notice here from the output plot here. It is rectangular for a start, and it has a width of 2 tau. So it's, if we say that the center point here, the middle or the peak of the triangle, the middle point of the triangle is some time instant, we'll just call it as tk. Then the one side of the triangle, that one extreme, is tk plus tau, and the other side is going to be tk minus tau. So the convolution operation doubles the length of the input parameters. That is, h of t is having a width of tau, x of t is having a width of another tau, and the convolution operation basically doubles it. So you see the width of this triangle is from tk minus tau to tk plus tau, so that entire width is 2 tau, right? The middle is tk, that's tau on one side, another tau on the other side, so the width is now tk. So that is the width of the output is double. That means it is spreading out the output. So we need to take care of intersymbol interference, because if the pulses are not spaced properly apart, then for two adjacent pulses, the outputs can overlap, resulting in intersymbol interference. Okay, so that's one observation that we need to bear in mind. The next observation we notice is that the peak of the output, that is the middle value, the peak value of the output, occurs after a certain delay from the peak value of the input. So the input, the central point, in the case of a rectangular, it has a maximum peak throughout the pulse, but there are other pulse shapes where the peak happens in the middle. So if we take this middle of the input pulse and compare it with the middle of the output of the matched filter, there is some delay. Okay, the peak of the output occurs after some delay of the peak of the input, and that delay is exactly equal to tau by 2. So there is a delay here, that is from the peak of the input to the peak of the output, there is a delay of tau by 2. So one of the disadvantages of a matched filter is that the output is delayed by tau by 2. So matched filter introduces some delay. Okay, and that is something we deal with. So as long as we ensure that the neighboring pulses have their outputs outside this Tk minus tau and Tk plus tau, then then there will be no intersymbol interference. So, and that is how we use the matched filter. So the output of the matched filter is 0 outside Tk plus tau and outside Tk minus tau. So to the left of Tk minus tau and to the right of Tk plus tau, the output of the matched filter is 0. So if we arrange our pulses to be spaced such that the neighboring outputs of the matched filter do not overlap, then we can have 0 intersymbol interference in a matched filter. So matched filter has no intersymbol interference. We can design our transmission in such a way, and matched filter does introduce some delay of tau by 2 for each of the pulses. So let's make those statements. Peak of matched filter output occurs tau by 2 seconds after the peak of its input. So we say that match filtering introduces delay. And the next point that we want to make is, if you notice from the diagram, the output of the match filter is 0 outside Tk plus tau and Tk minus tau. So we can have 0 intersymbol interference in matched filter. So matched filter output is 0 outside Tk plus tau and Tk minus tau. So therefore we say that matched filter excuse me, has no intersymbol interference. Which is ISI, intersymbol interference. The acronym is ISI. That is, it is because y of t equals 0 for t greater than Tk plus tau and for t less than Tk minus tau. All right, so for both these cases y of t is 0, and therefore it has no intersymbol interference. Now let's talk about what this tau equivalent represents. Okay, the tau equivalent that we have chosen here as the amplitude, 1 by tau equivalent is chosen as the amplitude of the matched filter impulse response. Now what does this tau equivalent represent? This tau equivalent is nothing but the energy of the transmitted pulse. So the energy of the transmitted pulse, so now we can write tau equivalent. Tau equivalent is set as tau equivalent equal to the energy of the transmitted pulse, which is p square of t dt integrated from minus infinity to infinity. Now for a rectangular pulse with amplitude 1, okay, then the amplitude p of t is going to be 1 for the entire duration of the pulse, and the duration of the pulse is from t0 to t0 plus tau. So the integral will be existing only in that limit, t0 to t0 plus tau, so which is integral 1 square dt. The amplitude is 1, so it's 1 square, which is dt from t0 to t0 plus tau. So that will give us t0 plus tau minus t0, which is equal to tau. So the tau equivalent is basically equal to tau, which is the width of the rectangular pulse. But if it is some other pulse shape, then it has to be the corresponding energy of that particular pulse. So tau equivalent is basically integral p square of t, and which is nothing but the energy of the pulse. So we can 1 by tau equivalent is nothing but 1 by tau, because tau equivalent is equal to tau. So what happens is basically the area of this impulse response is going to be tau into 1 by tau, which is equal to 1. So the reason why we set it this way is so that we want to normalize the energy of the impulse response. So h of t will be normalized to have area 1 under its impulse response, right? So by choosing the amplitude as 1 by tau equivalent, we can have this area under this impulse response to be equal to 1. So that's the reason why we scale the amplitude of the impulse response. Okay, so tau equivalent has been covered now. Now let us think about what happens if there is noise coming along with the transmitted pulse. So we want to measure what would be the output noise power at the output of the match filter. So if some noise, and we are going to restrict ourselves with the white noise. So we've been discussing about additive white Gaussian noise channel. So if additive white noise gets added with the pulse, and if that noise enters the matched filter, then what would be the noise power at the output of the matched filter? Okay, so the output of the matched filter that we have shown here is assuming that there is no noise. If the transmitted pulse is free of noise, then this is what we get, and that would be our received signal power at the sampling instant here. Okay, now we are interested in finding what would be the noise power at the output of the matched filter if there is noise entering the matched filter. So noise power at the output of matched filter So suppose our x of t gets added with noise, and the noise here we are talking about white noise. Well, that's white Gaussian noise. So if white Gaussian noise gets added with the transmitted signal, and we have the signal that is entering the matched filter at the receiver is the sum of the transmitted pulse x of t and the noise signal, which we denote as n of t, then the noise power at the output of the match filter, we are going to write it as NR is given as, in fact we can write that as sigma square also, because for white noise we have talked about sigma square, the variance of the noise being the representing the average power of random noise, right? So that's sigma square, and we can compute that from the impulse response or frequency response of the matched filter. So this is N naught by 2, which is the power spectral density of the noise, into the squared magnitude response, which is h of f square df. So h of f is nothing but the frequency response, or the frequency magnitude response of the matched filter. So we want to put that from minus infinity to infinity. So where, let me write that, where h of f is frequency response of matched filter. By the way, the frequency response is the Fourier transform of the impulse response. So we have the impulse response of the matched filter as h of t. So the frequency response h of f is nothing but the Fourier transform of the impulse response. So h of f is nothing but the Fourier transform or spectrum of the impulse response. So, but then we can write this as N naught by 2. We can replace the frequency response with the impulse response. It would give us the same result. So because they are linearly related, so minus infinity to infinity, integral minus infinity to infinity h of t squared dt. So this integral is equivalent. Okay, the two integrals that we have here are equivalent. So we can replace the matched filter frequency response with the matched filter's impulse response. When we are integrating here, it would give us the same result. So now we can write that as, so we can substitute, because we know h of t now, we can substitute the expression for h of t. So n naught by 2, and h of t is, with the rectangular pulse, it is 1 by tau equivalent p of td minus t, right? It is basically a rectangular pulse of width tau. So we simply write it as in the integration, it can simply be written as p square of t, because what matters is the limits of the integration. So n naught by 2, and we have 1 by tau equivalent. So we want to square this, right? H square of t. So 1 by tau equivalent p square of t. So because we are integrating it, whether we integrate it here or whether we have the pulse shifted and integrated here, the area under the pulse is going to be the same. So n naught by 2, we have 1 by tau equivalent as the scaling factor there, 1 by tau equivalent, and integral h square of t is nothing but integral p square of t from minus infinity to infinity, and integral p square of t from minus infinity to infinity is nothing but the tau equivalent which we had here, the energy of the pulse, right, which is what we had here. So this is basically equal to n naught by 2, 1 by tau equivalent into tau equivalent. So effectively what we have is, and by the way, this is squared, right? So it's p square, h of t square, so h of t squared 1 by tau equivalent square, right? So that's square there, which I missed out. Make that correction, please. And now, therefore, we have the output power of the noise at the output of match filter is n naught by 2 times tau equivalent. So the expression for the noise power at the output of a matched filter is n naught by 2 tau equivalent. So this noise power that we have at the output of a matched filter is the minimum noise power that we can have at the receiver output for any kind of receiver filter. So basically matched filter produces the minimum noise power at its output as compared to any other receiver filter. So match filter minimizes the noise power that comes into the receiver and gets processed, right? So that's the minimum noise power you can have, and that minimum noise power is obtained, the smallest value of the noise power is obtained when using a match filter. If you use any other kind of receiver filter, then the noise power is going to be at least as much as this or more than this, but never going to be less than this. So match filter minimizes the noise power at the output of the receiver because we want to minimize the noise as much as possible. So let's make that statement. Match filter minimizes the noise power at receiver output. So that's the minimum value that we can have, and that is given by this expression n naught by 2 times tau equivalent, where tau equivalent is nothing but the energy of the pulse. So integral p square of t, the energy of the pulse represents the tau equivalent. The next thing that we are going to discuss is another figure of merit for our digital communication system. Just as we have signal to noise ratio as measuring the signal to noise power ratio as measuring the ratio of the signal power to the noise power, in a digital communication where we have individual bits being transmitted, we need a much better figure of merit, so which compares the power or energy in a single bit with the power of the noise. So a good figure of merit that is used for a digital communication system is what is called as the bit energy to noise ratio. It's called as the bit energy to noise ratio, and we denote it as a term, say gamma b, which is defined as, okay, it is the triangle on top, means it's the definition. Okay, the figure of merit denoted as gamma b is defined as the bit energy EB divided by the noise power N naught. So it's called EB by N naught. That's a good figure of merit that is commonly used for a digital communication system. Now we are going to see what this looks like for our pulses of certain amplitude and having certain energy, and then we'll also get a relationship between this bit energy to noise ratio and the A by 2 sigma factor that we have been considering in our error probabilities. So we'll make a relationship between these two, and that way we can then rewrite the Q function in terms of the bit energy to noise ratio as well. So for that, let us consider that we are transmitting bits at a rate of RB bits per second. So consider, and again we are going to look at binary transmission here. Binary transmission at a rate RB bits per second. Okay, and since it's going to be binary, one bit is represented by one pulse, so it's each pulse is RB. So now suppose we are the transmitted signal has a certain power SR. We can write the bit energy in terms of SR and the bit rate. So if the transmitted if the signal power, let's be more general, if the signal power is SR, then we can write the bit energy, then bit energy, which is EB, is the signal power divided by the bit rate RB. So if we're transmitting RB bits per second and the average signal power is SR, then each bit will have an energy which is the signal power divided by the bit rate. So it's SR by RB, and therefore we can write the figure of merit gamma B. So this term gamma B, we can write it in terms of the signal power. So EB is SR by RB. We'll substitute it here. So we can write, therefore, this figure of merit gamma B is equal to SR by N naught times RB. So we have this relationship between the bit energy, the figure of merit for the digital communication system, and the signal to noise ratio SR by N naught. Okay, so we have this. Next, what we are going to do is we are going to compute the bit energy for some pulses which have a certain amplitude, which we'll denote as AK. So suppose transmitted pulses have an amplitude given by A subscript K. Okay, rather than 1, it can be any value. We made it equal to 1 with the rectangular consideration earlier just to simplify the analysis, but now we take it to a more general case where we have the pulses of arbitrary shape and having an arbitrary peak amplitude denoted by A subscript K. In that case, the bit energy, so then bit energy EB, okay, is equal to this AK. So we take the mean value of the squared AK squared, because if it's not a rectangular pulse, then the pulse will not have the same amplitude AK throughout the duration of the pulse. So if it is the same throughout the duration, then it's simply AK squared. But if it is some other shape where the amplitude is having a peak value of AK in the middle, and then it becomes lower away from the middle point of the pulse, then we define the bit energy as the average value of the squared peak amplitude. So it's AK square bar, the bar on top denotes average, into the energy, which is P square of T dt, from minus infinity to infinity. So that whole term basically represents the energy of the bit represented by that particular pulse of some arbitrary shape. Of course, the pulse shaping is a topic in its own right, but with the specific shape of the pulse, the energy per bit is going to be denoted by this term. So if we had this AK equal to 1, if it was a rectangular pulse with the AK equal to 1, then this term will disappear. We have simply integral P square of T dt. So, which is tau equivalent for the rectangular case, right? So it is AK square bar, which is the average, times integral P square, as we have seen earlier, is tau equivalent. So we have this representation for the bit energy when the transmitted pulse is having a peak amplitude of AK. Now, for our unipolar and polar cases, we can define what this AK square denotes. So this AK square, the average value AK square, is going to be, in the case of unipolar, a bit 0 is represented as 0 volt, and a bit 1 is represented as positive voltage, which is A. So this AK square is going to be half A square plus 0 square, right, which is 0. So which is equal to A square by 2, and that's for unipolar signaling. And for polar case, it is going to be half. In the polar case, the binary 0 and a binary 1 are represented with minus a by 2 volt and plus a by 2 volt. So the squared values will be a square by 4 and a square by 4. So it's a square by 4 plus a square by 4, so which is equal to a square by 4, which is for the polar case. Okay, so we now have what is this ak square term denoting for the unipolar case and for the polar case. Okay, and the bit energy is given by the ak square term into the tau equivalent, which is the energy of the corresponding rectangular pulse of unit amplitude. The next thing that we are going to do now is to get a relationship between this a by 2 sigma and the bit energy to noise ratio, which is Eb by n naught, and we are going to do that in the context of the matched filter, and we'll use this result of the matched filter, that the output noise power of the matched filter is n naught by 2 tau equivalent, which is the sigma square, right? So we're going to use this in getting that relationship. So let's start with this a by 2 sigma term that we are interested in, a by 2 sigma. And because we have sigma square as the noise power at the output of the matched filter, so we want to get this as a square term. So we'll square this entire term. So we'll square it. So that will give us a square by 4 sigma square. Now we're going to use sigma square, which is equal to n naught by 2 times tau equivalent, which is the minimum value of the noise power that is possible, and that minimum value is achieved using matched filter. So this n naught by 2 tau equivalent is the value that we have for a matched filter. And correspondingly, we can now write this a by 2 sigma the whole square, which is a by 4 sigma square. So in place of sigma square, we are going to put n naught by 2 tau equivalent. So we'll have it as a square by 4 n naught into 2 tau equivalent. So the 2 times tau equivalent will go in the numerator here. So we have this representation, which can be simplified as a square tau equivalent by 2 times n naught. So we're just considering the 2 with the 4 here, right? 2 will go here 2 times, so a square tau equivalent by 2 n naught. So that's what we have for the term a by 2 sigma the whole square. And now if you notice, this term here, the a square by 2 term here, is nothing but the ak square bar for unipolar case. So this a square by 2 is ak square bar, and this ak square bar into tau equivalent is nothing but Eb. So a square by 2 tau equivalent, this whole term becomes Eb for the unipolar case. And to make it for the polar case, we'll just multiply and divide by 2 so that we can write it for the polar case as well. So let's do that analysis now. So we'll first write down the expression for a by 2 sigma the whole square. A by 2 sigma the whole square is nothing but a square tau equivalent by 2 n naught. And since ak square bar is equal to a square by 2 for unipolar case, so this term a square by 2 is ak square. So you can write this as ak square bar tau equivalent divided by n naught. This is for unipolar, right? For unipolar, because a square by 2 is ak square bar for the unipolar case, as we have here. So ak square bar is a square by 2 for unipolar case. So now ak square bar into tau equivalent is generally Eb. So that is simply equal to Eb by n naught for the unipolar case. So this a by 2 sigma the whole square is basically a by 2 sigma the whole square is Eb by n naught for unipolar signaling. Or in other words, we can take the square root now. A by 2 sigma is going to be the square root of Eb by n naught for unipolar signaling. Right. Similarly, we will do the analysis for polar signaling. So I'm going to write down this expression again separately, and we'll do the calculation and get a relationship between a by 2 sigma and Eb by n naught for the polar case. So let's do it for polar signaling. So again, we'll write a by 2 sigma the whole square, which is a square tau equivalent by 2 n naught. Now for the polar case, that is in, let me write it separately. In polar signaling, this term ak square bar is equal to a square by 4, but we do not have a 4 in the denominator here, so to make a 4 there, we are just going to multiply and divide this by 2. So we'll make it, let's say, into 2 divided by 2. 2 by 2 is 1, right? So multiplying anything by 1 doesn't change its value. So now we can have this as 2 a square tau equivalent by 4 and naught. So now we have this term a square by 4. So we have this a square by 4, which denotes ak square bar for polar signaling. So we can write this a by 2 sigma the whole square as 2 times a square by 4 is ak square bar tau equivalent by n naught. So that is for polar signaling. Okay, now ak square bar tau equivalent is nothing but the bit energy that we have seen earlier. So for any arbitrary pulse shape, ak square bar into tau equivalent is the bit energy. So this term here, ak square bar tau equivalent, becomes the bit energy. So that will be 2 times Eb by n naught. So we can now, again, that is for polar signaling. Okay, so we can now write a by 2 sigma as the square root of 2 times Eb by n naught. So again, what we notice is that comparing unipolar and polar, this a by 2 sigma term, okay, in the case of unipolar, it is the square root of Eb by n naught, and for the polar case, it is the square root of 2 times Eb by n naught. So there's a factor of root 2 involved here. So in polar signaling, there is an SNR improvement of a factor of root 2, as we have seen earlier also when we analyzed it using a by 2 sigma. So that relationship remains the same. So we see that polar signaling has an advantage even in the bit energy to noise ratio in terms of by a factor of root 2. So if you recall, we had all our error probabilities, PE, denoted as Q of a by 2 sigma for the binary case, right? So which is nothing but Q of square root of Eb by n naught, that's for unipolar, and that's equal to Q of square root of 2 times Eb by n naught for polar signaling. So again, what we see is that polar signaling has an advantage over unipolar signaling by a factor of root 2. So I'm just going to write that statement here. So polar signaling has an advantage over unipolar signaling by a factor of square root of 2. Okay, so we come to the same conclusion, but what is important here is that we have made a relationship between A by 2 sigma, which was a representation of the signal to noise ratio for the communication system, and Eb by n naught, which is the figure of merit for a digital communication system where we are transmitting, we are interested in focusing on the individual bits. Okay, so we have a relationship between A by 2 sigma and Eb by n naught, and Eb by n naught is a common figure of merit that is used for a digital communication system. And one last thing that we are going to cover today is the relationship between A by 2 sigma and the signal to noise ratio itself. And we're not going to prove it, but rather just make the statement and give the expression, because later on we'll be using that expression in solving some numerical problems. So as I said earlier, A by 2 sigma is a measure of the signal to noise ratio. It is an indicator of the signal to noise ratio, but it is not the signal to noise ratio itself. So we want to give an expression or relationship between this term A by 2 sigma and the signal to noise ratio, which is SR by NR. So we'll make that relationship, because later on we are going to use that relationship in solving some numericals. So A by 2 sigma, as I said earlier, A by 2 sigma represents a measure of signal to noise ratio. Okay, it is not the signal to noise ratio itself. Of signal to noise ratio, which we denote as SNR, which is signal power divided by the noise power. Okay, that is signal SR by NR. So we want to just state the actual relationship between A by 2 sigma and the signal to noise ratio for a general MRE transmission. So, and that relationship is given as A by 2 sigma. So the relationship between A by 2 sigma and SR upon NR is as follows. So it's A by 2 sigma, the whole square. The square of that is equal to 3 by m square minus 1 by r times tau equivalent, where r is the symbol rate, not the bit rate. Okay, and tau equivalent is the width of the pulse that we discussed earlier. So it's 1 by r tau equivalent, and which turns out to be the energy of the rectangular pulse, and that gets multiplied with SR by NR. So that's the relationship between A by 2 sigma and signal to noise ratio. So the square of A by 2 sigma is given by this expression on the right hand side. Now we can further simplify this as for rectangular pulses, this term R times tau equivalent is equal to 1. And we've seen that earlier, okay, well, because the rectangular pulse, the impulse response for the match filter has an amplitude of 1 by tau equivalent, and the width is tau, and tau equivalent turns out to be equal to tau, so 1 by tau equivalent into tau, so the area becomes equal to 1. So this R tau equivalent term is equal to 1 for rectangular pulses. So therefore, in that case, we can write our A by 2 sigma the whole square as 3 by m square minus 1 times signal to noise ratio, which is SR by NR. And this term, A by 2 sigma the whole square, will be maximum when the noise power at the output of the receiver filter is minimum. When NR is minimum, that means signal to noise ratio will increase, and this whole term will also increase. So this will be maximum when the noise power NR is minimum, and the minimum value of NR will be achieved when using matched filter, and that minimum value is equal to N0 by 2 tau equivalent, which we have seen earlier. So the minimum value of the noise power, which is N0 by 2 tau equivalent, that is achieved for a matched filter. Okay, so this term will be maximum. So let's write that. This will be maximum when NR is minimum, and the minimum value of NR is equal to N0 by 2 times tau equivalent, which is achieved using matched filter. Okay, all right, we'll stop here for today, and we'll continue with the next topic, where we will do an example of a communication system, a digital communication system which transmits at a certain rate, and the signal to noise ratio on the channel is specified, and then we will also analyze the trade-off between the bit rate or the data rate and the error probability. So we will use this relationship between signal to noise ratio and A by 2 sigma, and because we need this A by 2 sigma term to compute our error probabilities. So based on the signal to noise ratio and the Emery transmission that we're going to use, we will analyze what is the bit error probability that we get for that particular scheme of transmission, and we'll see how increasing the value of M will increase the bit rate but also increase the error probability. So there is a trade-off in transmitting at a faster speed. Means there are going to be more errors in the received data, and we need to deal with those errors somehow. Okay, so we'll do an example on that in the next lecture.